Welcome, my dear students, to the topic 12.8 of thermodynamics. The topic is thermodynamic processes. Here we are going to differentiate different type of thermodynamic processes, and the lecture is going to be very wonderful today. So stay tuned and watch out every discussion. First of all, we'll see topic 12.8.1, that is quasi-static process. Name is quasi-static process. What is this? Let me elaborate. First of all, consider this figure. Here a gas system is given. Inside the cylinder piston arrangement, you can see here is a piston which can move, let us say, and it is surrounded by some atmosphere as it is shown here. Now for this arrangement, consider the gas in thermal and mechanical equilibrium. Let us say it is in thermal and mechanical equilibrium. That means what? When we say it is in thermal equilibrium, that means the temperature outside and inside will be same, and so no heat will travel inside or outside. As well as when we say mechanical equilibrium, that means the inside pressure and the outside pressure will be same, and so piston will not move any of the side, right? So here when we say it is in thermal and mechanical equilibrium, so obviously the pressure of gas and pressure of surrounding will be same, as well as the temperature of gas and temperature of surrounding will be also same. Now if we suddenly change the pressure of gas, the piston will move in either side. You can understand. Suppose if I increase the pressure of this gas system, then outside pressure is the same, the previous one, and the inside pressure has been increased. So obviously piston has to move outside. And vice versa, if I decrease the pressure of the gas, then the piston will move inside. Now if we change the temperature suddenly of the gas system, then heat will pass through either of the side. Suppose if I increase the temperature of this gas system, then outside temperature is less and inside is more, so heat will travel from the gas system inside to the surrounding. And vice versa, if I decrease the temperature inside, then heat will travel from outside to inside. Okay, so now it is understood that if we change the temperature or if we change the pressure, then the system will not remain in thermal equilibrium or in mechanical equilibrium, right? And during this, the gas, that means the system, will pass through non-equilibrium states. Try to understand this. When the piston is moving, so obviously pressure is continuously changing, or heat is traveling inside to outside or outside to inside, whatever, the temperature is continuously changing, and so it is not an equilibrium state, it is rather a non-equilibrium state of the system. Now there is a little problem with this type of non-equilibrium state, that such type of non-equilibrium states of system are difficult to deal with, because we cannot apply thermodynamic state equations and so on. See, when the system is in non-equilibrium state, then pressure, temperature, volume will be rapidly changing, right? So you cannot apply thermodynamic equations there. So you cannot define this type of non-equilibrium systems. Therefore, it is convenient to imagine an idealized process which is infinitely slow. Are you getting this? We have to imagine a process which is obviously idealized process, in which the process is taking place very slow, infinitely slow. Alright? That's why the changes in the variables like P, V, T is very slow. Thus, the system remains almost in thermal and mechanical equilibrium with the surroundings throughout the process. Look, if we take the process to be very slow, that means infinitely slow, so what will happen? The variables like pressure, volume, temperature will be varying, but they will be varying very slow. Okay, it will be varying very slow, and so at any moment of time, if you see, you will find that P, V, T are almost constant. For a short time interval, we can say the P, V, T will be found almost constant, and so for that short time interval we can say that the system is in thermal as well as in mechanical equilibrium. This way, throughout the process, at any moment, any point, we can say that the system is in thermal and mechanical equilibrium. So, by this type of assumption, or say this type of idealistic imagination, we can take the process to be in thermal equilibrium and mechanical equilibrium throughout the process. Alright. So, such type of process is known as quasi-static process. I repeat, when we consider any process which is moving very slow, infinitely slow, in that condition, it can be considered as in thermal and mechanical equilibrium, and such type of process is known as quasi-static process. Now the point is, why we are discussing this quasi-static process at all? Because it is not like that every process will be found in thermal and mechanical equilibrium always. If the process is not in thermal or mechanical equilibrium, that means if the process is in non-equilibrium state, then we have to consider that process as quasi-static process, so that we can apply the thermodynamics laws, we can apply the thermodynamic state equations. Understood? Obviously, quasi-static process is a hypothetical construct, but we can apply thermodynamic state equation to such processes, and so we shall now deal with quasi-static processes only. As I discussed, that quasi-static process is basically hypothetical. It's not real. Alright, it's an ideal thing. We are assuming a process to be quasi-static process, but the benefit is that we can apply thermodynamic state equations to such processes, and that's why we shall now deal with such type of quasi-static processes only throughout the chapter. Alright, now let's move forward. Now after we are going to discuss about some special thermodynamic processes. These processes are isothermal, isobaric, isochoric and adiabatic. Here in isothermal process, temperature remains constant throughout the process. In isobaric process, pressure remains constant throughout the process, and in isochoric process, volume remains constant throughout the process, and in adiabatic process, heat remains constant throughout the process. That means no heat flow between the system and the surrounding. That means delta Q, that is the transfer of heat, becomes 0. Okay. Now before we move forward, let me clarify one thing here to you students, that isothermal and adiabatic are entirely different thing. When we say isothermal, so temperature remains constant, but in this process heat may pass from system to surrounding or surrounding to system. Alright. And when we talk about adiabatic process, that means heat remains constant, but in this process temperature may increase and may decrease too. Yes, in adiabatic process heat is remaining constant, but the temperature of the system may increase or may decrease too. Alright, so that is the difference between isothermal and adiabatic. Now let us move forward to the topic 12.8.2, and that is isothermal process. Now when we say isothermal process, that means temperature remains constant, so T is constant. Now if you use ideal gas state equation, then obviously PV is equal to mu RT. Alright, but mu R and T is also constant, that means PV is going to be constant. This is very important for any isothermal process. Also here, because the temperature is remaining constant, so the internal energy of the system will also remain constant. We know that internal energy depends on temperature. If temperature changes, then only internal energy will change for the ideal gas. So here temperature is constant, so obviously internal energy will remain constant, and so change of internal energy, that is delta U, will become 0. Now if you take delta U is equal to 0, then as per thermodynamics first law we can write delta Q is equal to delta W. Now this means something very important. This means that delta Q, which is the supplied heat to the system, and delta W, here delta W is positive, So it is the work done by the system. So this shows that the heat supplied is equal to the work done by the system. So that is written here. Thus the heat supplied to the gas equals to the work done by the gas. Delta Q is equal to delta W, means heat supplied by the gas is equal to the work done by the gas. Mind well, it is by the gas. Now you know the work equation. Work delta W is equal to P delta V, right? Here if we take delta V tends to limit 0, that means if we take delta V infinitesimally small, then we can write dV at the place of delta V. So now the work equation becomes dW is equal to P dV. Now if you want the total work during the entire process, then we have to take integration of all this type of dWs. That means the total work W will be equal to integration of dW, that means it is integration of P dV. Here we are integrating with respect to volume, so we should take the limits of volume by putting here V1 and V2. V1 is the initial volume, V2 is the final volume. Now using the equation PV is equal to mu RT, we can write P is equal to mu RT upon V, right? P is equal to mu RT upon V. So at the place of P, I can write now mu RT upon V, and here is dV. But because this is an isothermal process, so we can take this mu R and T all as constant and can be kept outside the integration. So remaining is integration 1 upon V dV. Now from the integration rules, you know that integration 1 upon V dV becomes ln of V. Here you know that ln is log to the base e, right? Ln of V, and the limits are V1 to V2. Okay. So now you have to put this upper limit and lower limit, so it will become ln of V2 minus ln of V1. But ln of V2 minus ln of V1 can be written as ln of V2 upon V1. So finally the work equation in isothermal process becomes W is equal to mu RT ln of V2 upon V1. Now there is an interesting discussion we can do from this equation. You might be aware of one thing, that if the term inside ln, inside this log, is greater than 1, then the answer of log will be positive. If the term inside this log is less than 1, then the answer of this log will be negative. Okay. So in isothermal expansion, when V2 becomes greater than V1, see, we are talking about expansion. So obviously the final volume V2 will be larger than the initial volume V1. So V2 is larger than V1. So obviously V2 upon V1 will be larger than 1. And so we can say ln of V2 upon V1 will be greater than 0. As I said that when V2 upon V1 is greater than 1, then ln of V2 upon V1 will be positive, that means it will be greater than 0. Now this gives that W will be greater than 0, because ln of V2 upon V1 is greater than 0, that means W, the work, will be greater than 0, or say the work will be positive. This shows that in isothermal expansion work is positive, so obviously it is work done by the system. I hope you remember that when the work is done by the system, work is positive. Okay. And this work is equal to the heat absorbed by the system. This work, which is work done by the system, is equal to the heat absorbed. Why it is so? Because we know that for isothermal process, Q is equal to W. Q is equal to W. That means the heat absorbed will be equal to the work done. So in isothermal expansion, the whole process is taking place something like this, that the heat is absorbed by the system, and by that heat the system is doing work, and the work is equal to the heat absorbed obviously, and when the system is doing work, so it is expanding, and that's why it is isothermal expansion. Alright. Now the opposite is also true for this case, that is, in isothermal contraction, work is done on the system, which is equal to the heat released by the system, because it's a case of isothermal contraction. So obviously what is happening here, the work is done on the system and the heat is released by the system. Now let us see topic 12.8.3, that is adiabatic process. Now when we say adiabatic process, that means the heat remains constant inside the system, the heat remains constant. Obviously for that you have to take an adiabatic wall or say non-conducting wall around the gas system. Okay. So the point is that in adiabatic process Q is constant. That means delta Q, that is the heat exchange, will be 0. There will be no heat exchange because the walls are adiabatic, walls are non-conducting. Now because delta Q is 0, so as per thermodynamics first law we can say that delta U plus delta W will be also 0, and thus we can write that delta U is equal to minus delta W. This shows that when delta W will be positive, delta U will be negative. So this indicates that in adiabatic process, work done by the system, that means when the work is positive, decreases the internal energy of the system, means delta U becomes negative. So in adiabatic process, if the work is done by the system, then internal energy will decrease, and vice versa. If the work is done on the system, then internal energy will obviously increase. Now here is one very important equation that you have to just accept without any proof, and that is for adiabatic process PV raised to gamma is constant, where gamma is Cp upon Cv, means gamma is a ratio of Cp, that is molar specific heat at constant pressure, and Cv, that is molar specific heat at constant volume. Remember that gamma will have a value greater than 1. So for adiabatic process you have to remember that PV raised to gamma is constant. So in general we can write that PV raised to gamma is equal to P1 V1 raised to gamma is equal to P2 V2 raised to gamma is equal to some constant C. This C is a constant here, right? Now the total work in the process can be written as W is equal to integration V1 to V2 PdV. But from this equation, see, PV raised to gamma is equal to C, right? So from this equation we can write P is equal to C upon V raised to gamma. So at the place of P I am putting C upon V raised to gamma. C is a constant, so I have taken out, and then integration 1 upon V raised to gamma dV is remaining there. Now this V raised to gamma in numerator can be written as V raised to minus gamma. So the equation becomes W is equal to C integration V raised to minus gamma dV from V1 to V2. Now we can integrate this V raised to minus gamma. The answer will be V raised to minus gamma plus 1 divided by minus gamma plus 1, right? In integration you know that you have to add 1 in the power. So here the power is minus gamma, so I am adding plus 1, and here also in the denominator you have to put the new power, that is minus gamma plus 1, and the limits are V1 and V2. Now we have to place V2 at the place of V, then minus, then we have to place V1 at the place of V. So the equation becomes W is equal to C, this is V2 raised to 1 minus gamma minus V1 raised to 1 minus gamma, and in the denominator we are having 1 minus gamma. Say at the place of minus gamma plus 1, everywhere I have placed 1 minus gamma, right? Now I am multiplying this C inside the bracket, so I will get 1 upon 1 minus gamma C V2 raised to 1 minus gamma minus C V1 raised to 1 minus gamma. But as we have discussed here, that C can be written as P1 V1 raised to gamma or P2 V2 raised to gamma as well. So now watch clearly. At the place of C here, I am putting P2 V2 raised to gamma, and at the place of C here, I am putting P1 V1 raised to gamma, because C is P1 V1 raised to gamma as well as P2 V2 raised to gamma. So here I am placing P2 V2 raised to gamma, here I am placing P1 V1 raised to gamma, and the remaining terms are as it is. here V2 raised to 1 minus gamma is there as it is, and here V1 raised to 1 minus gamma is there as it is. Now obviously V2 raised to gamma and V2 raised to minus gamma will be cancelled out. V1 raised to gamma and V1 raised to minus gamma will be cancelled out. So the remaining term is P2 V2 minus P1 V1. So here it is W is equal to P2 V2 minus P1 V1 upon 1 minus gamma. Also, as per the ideal gas equation, we can write P2 V2 is equal to mu RT2 and P1 V1 is equal to mu RT1. Here mu R is common, so we can write the final equation of work, that is work W is equal to mu R T1 minus T2 upon gamma minus 1. Note that here when you take mu R as common, you will get T2 minus T1 in bracket, and in the denominator you are having 1 minus gamma. So I have flipped the terms, both of the terms in numerator and denominator. At the place of T2 minus T1 I have written here T1 minus T2, and at the place of 1 minus gamma here I have written gamma minus 1. So finally the work equation becomes mu R T1 minus T2 upon gamma minus 1. Okay. Now here the difference of temperature, whether it is positive or negative, will decide whether the work will be positive or negative. Let us see. I have just repeated the equation here. W is equal to mu R T1 minus T2 upon gamma minus 1. Now here if T1 is greater than T2, that means the initial temperature is larger and final temperature is less, means the temperature is decreasing. Then obviously from this equation we can say if T1 is greater than T2, then the work will be greater than 0, means work will be positive. Now when the work is positive, we can say it is work done by the system. So in adiabatic process, when the work is done by the system, means the work is positive, the temperature decreases, means T2 becomes less than T1, and vice versa. If the work is done on the system, means if the work is negative, then temperature increases. That means the final temperature will be larger than the initial temperature. Now let us see two graphs of P versus V, pressure versus volume graph for expansion and contraction, especially for isothermal and adiabatic process. Students, these are two very important graphs you have to understand and then you have to remember as well. See, the first graph is of expansion, means the volume of the system increases from V1 to V2. Now, if this expansion takes place in isothermal process, then the graph will be this way. Okay, but in adiabatic expansion, the graph will be this way. You can see the adiabatic graph is having more curved graph than isothermal graph. Moreover, you can also see one more big difference, and that is, see, this is the initial point, right? So let us say the pressure is P1 here, and for isothermal process the final pressure is P2, whereas for adiabatic process the final pressure is P2 dash. Now you can see that initially pressure was same in isothermal and adiabatic process both, but after expansion the pressure of isothermal is more than the pressure of adiabatic, whereas the volume is the same. Make sure that the final volume in both the processes is the same, and that is V2. But the pressure, the final pressure is P2 in isothermal and P2 dash in adiabatic, where P2 is larger than P2 dash. That means for the same amount of expansion, we are getting different final pressure for isothermal as well as adiabatic processes. Now let us see case of contraction. Suppose we are contracting the same system from V2 to V1. We are bringing it back from V2 to V1. In this case, here is the adiabatic process and here is the isothermal process. Here also you can see that initial pressure is, let us say, P1, then final pressure for both isothermal and adiabatic is different. For isothermal, let us say it is P2, and for adiabatic, let us say it is P2 dash. We can see that P2 dash is larger than P2. So here also, for the same amount of contraction, we are getting different final pressures. Here, don't forget to note one thing in expansion and contraction, that the graph of isothermal and adiabatic has been flipped. See, here in expansion, the upper graph is of isothermal and the lower one is of adiabatic. But in contraction, the upper graph is of adiabatic and the lower graph is of isothermal. Also note one thing, that in both the cases, the curve of isothermal is less, whereas the curve of adiabatic is more. Now let us see topic 12.8.4, Isochoric process. Isochoric process means when the volume V remains constant. Now if you put the volume V constant, that means you cannot move the piston, and if you cannot move the piston, that means there will be no work done. So delta W will be also 0. Now because delta W is 0, the first law of thermodynamics can be now written as delta Q is equal to delta U. Delta Q is the heat absorbed and delta U is the increase of internal energy. So we can say that in isochoric processes, the heat absorbed by the gas goes entirely to increase the internal energy of the system, and so to increase the temperature of the system as well. Let me repeat this. In isochoric process, whatever heat is absorbed by the system goes to increase the internal energy of the system, and because the internal energy is increasing, then obviously the temperature will be also increasing. Now let's see topic 12.8.5, Isobaric process. When we say isobaric process, that means the pressure P remains constant. In this situation, we already know the work equation. So the work done by the gas system can be written as W is equal to P delta V, or at the place of delta V we can write V2 minus V1. Now if I multiply this P inside, I will get here PV2 minus PV1. Now from the ideal gas equation we can write PV2 as mu RT2 and PV1 as mu RT1. Now taking out mu R common, we can get W is equal to mu R into bracket T2 minus T1. This is the work equation for isobaric process in terms of temperature. Here the heat absorbed partially goes to increase the internal energy and partially goes to do work by the system. See, in isobaric process, whatever heat is absorbed by the system is divided into basic two parts. One part goes to increase the internal energy, because the temperature is increasing, so obviously internal energy will be increasing, and another part goes to do work by the system. Here the work is done by the gas system. Okay, so the total amount of heat absorbed is divided into two parts. One is in increasing the internal energy and one is in doing work by the system. Finally, let's see topic 12.8.6, that is cyclic process. In cyclic process, the system returns back to its initial state after passing through many intermediate states. Means a cyclic process is such a process in which the process passes through many intermediate states, but finally it returns back to the initial state itself. Means if the initial pressure, volume and temperature of the system were P1, V1, T1, then finally also its pressure, volume and temperature becomes P1, V1, T1. Now because here T initial and T final are same, means the initial temperature and final temperature are same, so there is no change in temperature, and that's why there will be no change in internal energy as well. So change of internal energy delta U will become 0. Now as per thermodynamics first law, we can write delta Q will be equal to delta W only, because delta U is 0. Now delta Q is equal to delta W means what? Delta Q is the heat absorbed by the system and delta W is the work done by the system. So we can say that here in cyclic process, the total heat absorbed by the system is equal to the work done by the system. Obviously, from this equation we can say the total heat absorbed by the system will be equal to the work done by the system. Just for a reference, here is P versus V graph of a cyclic process. You can see here the process starts from point 1. Then from point 1 to 2 it goes in isothermal expansion. Then after from point 2 to point 3 it goes in a adiabatic expansion. Then from point 3 to point 4 it goes in a isothermal contraction, and from point 4 to point 1 it goes in a adiabatic contraction. So finally the process reaches to the initial point 1. So this becomes a cyclic process, and in this cyclic process delta U will be 0, right? So finally I stop this lecture here. Today we have learned about thermodynamic processes, like 5 processes mainly: isothermal process, adiabatic process, isochoric process and isobaric process. Along with finally we have studied the cyclic process as well. For your convenience, I have prepared a PDF of all the writing work that I have done today, and I have kept that PDF in the description box. You can download it and can write from that also. I will also like to remind you that all the equations that I kept in a bracket are very important. I would like that you better note it down in a different notebook and prepare these equations, because these equations are going to be very much useful in all the numericals as well as in all the MCQs. Alright, so herewith taking your leave, signing off, Anshuman Baldania.